2.3 is all about continuity. And that sounds maybe kind of weird. But first of all, this is our definition. So if you want to pause video, kind of write this stuff down. But it does differentiate between the interior point and the exterior point. So interior, inside the end, well, let's maybe start with the exterior. An exterior basically said if we have a left endpoint, it is continuous only here. As we come, left endpoint is going to be the right side. We can only come in from the right side because there's nothing on the left side. The right endpoint, because notice that the left endpoint A, this is A from the right. It's continuous at the right endpoint B, B from the left. So B is only from the left because there is no right side of the endpoint. So it says inside that it's continuous whenever the limit equals the y value. So we've kind of talked about, and I'll get into this more on the next page, I think. Notice that x equals 1, the limit does not exist because the left does not point to the same place as the right. The limit from the left is not equal to the limit from the right. So what this says is the limit does exist, so we can't say it's continuous at 1. At 2, the limit from the left equals the limit from the right. So the limit exists, but the limit is different from the y value. So then this part isn't true. So basically, it's continuous everywhere that you just don't pick up your pencil. You don't pick up your pencil. As soon as you have to pick up a pencil, which includes a hole, so continuous, 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 not continuous because you got to pick up your pencil. Not continuous to put your y value. Continuous, continuous, continuous. All right, so let's summarize that. So let's say it's continuous at x equals 0 because this is an endpoint and it equals the y value. So the limit as x approaches 0 from the right equals f of 0. So when the graph is pointing to the actual y value, it exists. How about at 1? Notice at 1, the limit from the left does not equal the limit from the right. So x equals 1, there is a point of discontinuity because the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. Okay, how about at 2? Is it continuous or discontinuous at 2? Well, first of all, the limit from the left equals the limit from the right, but does the limit equal the y value? No. That's why x equals 2 is a discontinuity. The limit as x approaches 2 equals 1, but the y value at 2 is 2. See how these are different? So our reason is the limit as x approaches 2 does not equal f of 2. How about 3? At x equals 3, it's continuous because the limit as x approaches 3, it exists, and it equals the y value at 3. So the limit from the left is 2. The limit from the right is 2. the y value is 2. If all three of those values are the same, it is continuous. So there's an easy way to think of continuity, and then there's the way you have to actually defend why it is continuous. This is the way you have to say it to prove that it's continuous. And that'll take us a little bit, and then we'll keep working on it. Okay, so let's look at this. Is it continuous? This is our int x, greatest integer function, step function. Is it continuous here from the left? It's continuous everywhere until I get to 1, and then it jumps. Everywhere between 1 and 2, then it jumps. Do you notice that it is continuous at all places except integer values? Everywhere but integer values. Okay. Let's see if I want to word that any. Okay. Yeah, the only way I put it in my notes was it's continuous at every non-integer value. So that works too. Okay. There, you've got to fit 4 slides into that little space at the bottom. So this is like one slide. You got to fit teeny tiny graphs, just so you know. Both of these are considered removable. Removable is if you can remove the discontinuity. So see how the limit exists, but it doesn't equal the y value? We could remove the discontinuity by just dragging the solid point and dragging it down to fill in the hole. If there's no y value, we just fill in the hole, and that would remove the discontinuity. So if you see any type of a hole in your graph, it is a removable discontinuity. Okay, hole implies removable. And remember, if you're not looking at a graph, how do you know there's a hole in the function? That's when a factor cancels from top to bottom. This is one type. The second type we talked about in class, the jump. If you remember, well, the one we talked about, this was open at the top too. There's no way that we could remove this continuity because the limit from the left does not equal the limit from the right. See back here, the limit exists. The limit as x approaches, let me just say c, exists, but it does not equal the y value at c. So the limit exists, but it doesn't equal the y value. In a jump, the limit as x approaches c from the left does not equal the limit as x approaches c from the right. So basically, the limit does not exist in a jump discontinuity. The third is if there's a vertical asymptote. All right, a vertical asymptote is an infinite, which would make sense. There's infinity, it goes infinitely up and down. If there's a vertical asymptote, that's an infinite discontinuity. How do you recognize a vertical asymptote in a function? That would be if there's an x in the denominator that's not a whole, but a value that would create a 0 in the bottom. That's not a whole. And we'll see that later. All right, let me just tell you right now, the fourth way, you're never going to see. but we have to at least talk about it. It's when it's like so busy in the middle that you can't even tell what it's going towards. And we never ever even talk about it. So, okay. So this is going to help hopefully figure out the different types according to the function. All right, so just looking at the picture, it's easy to tell where there's an asymptote and where there's a hole. We have to be able to do the same thing by looking at the equation. So the very first thing you're going to do is you're going to factor. So I can definitely see how to factor x squared minus 9, just x plus 3x minus 3. And I've got to know if there's a hole, that means one of these two go in evenly into the top. So I'm going to use synthetic in order to see if they work. All right, so remember when we put either 3 or negative 3 into the top corner, I look at x to the third, that's coefficient is 1. This is my x to the third. There's no x squared, x, and my constant. Remember, if there's 3, if your degree is 3, you should have 4 numbers across because your x is including your constant. First step is I'm going to drop the first coefficient straight down. Then I'm going to multiply 3 times 1. Then I'm going to add 3 times 3 is 9. Add 2 times 3 is 6. And if you get a remainder of 0, you know that x minus 3 goes into this polynomial. All right. So that means that x minus 3, I can factor x minus 3 out, and this is my leftover. X squared plus 3x plus 2. So with this process helps us see if I take x minus 3 times x squared plus 3x plus 2, I get this polynomial. Okay, so now is there any factors that we can cancel from top to bottom? X minus 3. Because there is a hole at x equals 3, there is a removable discontinuity. Ooh, I don't know where. All right. Then this is left. This didn't cancel. That tells me there's a vertical asymptote at this spot. X equals negative 3 is a vertical asymptote. If there's an asymptote, that's an infinite discontinuity. So you've got to make the connection. If something cancels from top to bottom, that's a hole, therefore removable. If something is still left on the bottom, that's a vertical asymptote, therefore it is infinite. All right, so we're going to graph this now. First of all, asymptote at negative 3. All right, there's a hole at positive 3. I got to figure out what that y value is. So I'm going to plug the 3 in to what's left here. So if I plug 3 in, that's 9 plus 9 plus 2, that's 20 over 3 plus 3 is 6. 26 or 10/3. So that's 3 1/3. So that means there's a hole at 3 1/3. All right, now let's consider the end model behavior. our end model behavior is what the graph is doing at the ends of the graph. So we kind of disregard everything except our power function. If I have x to the third over x squared, we're left with y equals x. So what that means on this side and on this side, it's going towards y equals x. So if I'm coming, so that means this is going this way. I got to swoop down. Okay, let's plug 0 in for x to figure out another coordinate point. If I plug 0 in for all of the x's, I get -6 over -9. That's 2/3. So this point has a point right here. So it kind of just bounces like that. And this, I've got to use my ends here and my ends here. Got to connect my points. And when the denominator, if this exponent at x plus 3 is just a plain x plus 3, not squared or anything, that means one side's going down and the other side's going up. So we can put all those pieces together to graph it. All right. So this says, let's write a function so that previous function is continuous everywhere except where there's a vertical asymptote. So, okay, I'm going to use g of x here because we're already using f of x. We're going to use a piecewise function, and I'm going to write the original function for the first part of my graph. Now, where's the one spot that we're taking out the discontinuity? Because we're saying we know we can't fix the vertical. The only part we can fix is when x equals 3. So what I'm going to say, I'm going to use this graph for everywhere except 3. For everywhere except 3, we'll keep that graph. Then, when x equals 3, I'm going to fill in the hole with the value, the y value that we found when we plugged 3 in. What this does, if I assign that to the function, I'm going to fill in that hole so it's now continuous. When you fill in a removable discontinuity, it takes away the discontinuity. All right. Basically, this just says a function is continuous on an interval if and only if it's continuous at every point of the interval. Well, that would make sense. A continuous function is one that it's continuous at every point of its domain. Now, so we want to make a distinction here. If I have 1 over x, I can see there's a vertical asymptote at x equals 0. But see, because 0 is not a part of the domain, it doesn't count against the function itself. We say there is a discontinuity, but we say that the function itself is continuous because the only point of discontinuity isn't in the domain. So yes, it's a continuous function. All right, this wants you to write out the properties that, this is like the third time of writing out the properties of limits. The properties of continuity are the same as the limit properties. All right, this just says composites of continuous functions are continuous. All right, so for example, say that f of x equals x squared. This just the x squared. And g of x equals sine of x. So let me just make it real simple, continuous means that you can just draw the graph without picking up your pencil. So if you think of x squared is continuous everywhere. There's no hole, there's no break, there's no jump, there's no asymptote. It's all continuous. Sine of x, continuous forever and ever and ever. If x squared is continuous and sine is continuous, then sine of x squared is continuous. Same for the second one. Is cosine continuous? Say g of x is cosine is continuous. F of x is the absolute value of x, absolute value is continuous. So if each of these are continuous separately, if we plug them into each other, that will also be continuous. And this is the same thing. This is just breaking it apart by multiply, divide, add, composite. If all the pieces inside are continuous, then it is continuous. Okay, so notice this has a lot of stars. It even has Spanish. Boy, this is super, super, super important. So take a minute, pause the video, write down the theorem, and then I'm going to talk about it. Okay. So first of all, we talk about a function that is continuous, highlight continuous, and on a closed interval. In order to use the intermediate value theorem, you have to first say closed and continuous. All right, so what this is saying, say I have some point over here where my x coordinate is a, so then the point is a f of a. I'm going to plug in my x coordinate and my y coordinate is f of a. Then I'm going to come over here to my x coordinate b. Then this coordinate is b, f of b. So if it is continuous and closed, in order for me to connect this dot and this dot, I'm going to hit every single y value between this y value and this y value. When I connect the dots, no matter how I connect the dots, if it's continuous, that means this y value is represented, this one, they're all represented. Every y value between this one and this one. So then an application is any real number exactly one less than its cube. So do we know what the number is? No. Anytime we don't know a number, we're just going to use the number x. Exactly equal to 1 less than its cube. So x cubed minus 1. Is there any number exactly equal to 1 less than the cube? So the easiest way to do this, I am going to set this equal to 0. And I'm going to graph this particular function. Okay, and when you graph this equation, it crosses the x-axis somewhere between 1 and 2. So that means that there is an x value that equals 0. That's a solution to this equation. Because this value right here tells me where this equation equals 0. And I didn't graph it for some reason, but If you graph it on your calculator, I just made a note that it crosses somewhere between 1 and 2, so yes, there is.